You're earlier than the ring. Supposed to. You want me to already start now? I promise you, the moment I start, it's going to ring. This is just Murphy's law. There you go. Welcome back. So let's continue with this. So we were with the expression tree that is also called a query plan in databases. It's basically a plan of action. What is the strategy to execute the query and give a result to the user? Now we are in the optimization phase that is just repeating. We just look for inefficiencies and modify this query plan in order to make it better and better and better. There's many technologies for that I'm not getting into, but basically you just come up with a better query plan. And then once you're done, there's something called code generation, where you turn this query plan into a tree of runtime iterators. So this is where the action actually happens. So these are actual objects in memory in Java, or in that case, it's Java. And what happens is that right here, that's the top level, you pull the string and pull the items out, right? So you all the items, and it basically draws them from as the flow, like bottom up, right? So this is how it works. This is the actual runtime. This is what's actually going to be executed. I'm going to give you now more details about that. But this is, again, the runtime part. This is still compile time where we have that. It's a query plan and the runtime. This is not just for RumbleDB, it's very common, right? Many database engines, including relational database systems, they are implemented in this way. Now, what's going on in this runtime iterator tree, right? The last one that gets executed. What is the data that flows? Well, most of the time it's going to be sequences of items, right? Whenever you have expressions, it just flows sequences of items. You see, sequences of items. Every time I have a black edge here, that's basically a sequence of items that flows. But there is an exception. Between clauses, within the flower expression, between clauses, we don't have sequences of items. We have, what is it that flows between the clauses? Tuples, yes. So more exactly. So tuple and then streams, yes, I heard it. Tuple streams. Yeah, so it's a stream of tuples or a tuple stream. And so basically, since here we have a for, so that's a clause, out of a clause, you output the tuples, the variable bindings, right? So we have a stream of tuples. So this is why this one I put in red. But again, a for clause is not an expression. That's why it's not a sequence of items. Expressions, it's always a sequence of items. But basically, we have this gigantic runtime iterator, and then we have the sequences of items and the streams of tuples that flow through it. Now, how do we do that? Because the data is flowing, so you probably visualize in your mind how the data nicely flows through that graph. But what happens in reality? Because in reality, we need to have this executed on top of the CPU on the machine, right? We need to implement it in an imperative language, like Java in that case, could be C++, could be Python, any other language. So yes, we implement that in an imperative language, but again, we do it just once, because the actual users of the system will not see that imperative language. So the idea of the imperative language is we, the engineers, go through the trouble of implementing all of that imperatively so that the end users don't need to bother with that. They can just ask on a high level. So what happens in our imperative language, like in Java, when we try to implement that? So in Java, I have my for iterator that produces a stream of tuples, and I have a return iterator that's going to produce sequences of items. So here is my tuple stream right here. I have the variable $i that every time gets bounced to a single item, a sequence of one item. Could be more in general, but just in that case. So what happens? There are multiple ways of doing that when you propagate the flow of data. One way is to have all of these tuple. At some point, it's like the customs. You put some stop shield, and you just pull the string here and let them come, but you just accumulate them in memory. So at some point, in memory, you have pulled up all of your tuples, and you're done. At some point, there is some signal that it's done. But it's all accumulated together in memory. This has a name. It's called materialized. What we've just done is materialized this tuple stream as a list of it's actually a list in Java of these tuple streams. And then we can evaluate the return expression and just then in that case, assuming that I'm just returning the integers here, then I'm going to just iterate on the list and then return that. But again, you saw we just put some sort of DAM here and then we just accumulate that. And only when we have them all, we forward that. Now it works because it was just 6. But now imagine what happens if you have a billion of them or even a trillion of them, right? At some point, the memory becomes full, right? So it's going to reach the limits of the machine. But in some cases, you can actually go the Netflix way. What do you do when you watch Netflix? Does it download the entire episode of the series? No, it doesn't. It downloads the first seconds, then you watch them, and then it's going to download the next 10 seconds and so on and so on and so on, right? So we go the Netflix way and we stream. It's the same, it's even the same words. So it's called streamed execution. So we Netflix our way through the data. We take one, we already output the one here. Then we are done. We delete it, freeze memory. Take the second one, output, third one, output, fourth one, output, fifth one, output, and that's it, right? So now we can do it forever. It doesn't even matter how many tuples we have. We can go for years like that, right? And it would have, as a materialized execution, it would have exceeded the memory of the machine. But Netflix, you can watch an entire year's worth of series, even if it's more data than what fits on your laptop. You don't care. You only need the seconds that you're currently watching in your memory. So this is called streamed execution. The problem of streamed execution, even though you can process more data than fits in the memory of your machine, because you always throw away once you're done, it can take a lot of time like this, because it's still sequential, right? We process the tuples one by one. So it's going to take time. What do we do in order for it not to take time? We can parallelize. Yes, absolutely. See, now I'm going to basically divide it into, I have put a few on the left, a few on the right. Okay, I was very shy with parallelizing here on just 2 computers, but you can do it with 1,000 different machines. So we parallelize like this, and we just do it in parallel. So on the first machine, I'm going to process the first 2, on the second machine, the other 3 at the same time. And at the end, I just put it back together, right? So this is the magic of parallelization. So now, not only don't we have any space problem anymore, but we also don't have any time problem anymore because we spread it over the machines. Now, that was a simple case. So in that case, I could decide if I can stream, if I can parallelize, if I can materialize, you know, I had a choice. You don't always have that luxury. For example, if you try to evaluate an order by, do you think you can stream? Who thinks you can stream an order by? Who think you cannot stream an order by? Why? Yes, maybe the microphone, if we can try to, small hops. There you go, right? You need to wait for a few seconds,
yeah.
Yes?
We have to look at the whole set of data to order by.
Exactly.
That's the reason.
That's exactly it. Imagine that you have a sequence with 1 billion values that are anxious to be sorted, right? And you need to figure out the first value that comes out of that. Do you realize that unless you have seen everything, you cannot tell what the first value is going to be? For all you know, it might be the last one, right? So that's the reason. For sorting, you have no other choice. You cannot stream that, but you can parallelize. Who heard of merge sort? Can you imagine parallelizing merge sort? I see a lot of, yeah, raise your hand. Okay, so it's basically merge sort. You can do it in parallel, but you cannot stream. This is the one thing. So you really need to think every time, can I stream? Can I not stream? Can I parallelize? Can I not parallelize? It really depends. And the nice thing is that RumbleDB figures it out. Sometimes it figures out that it can stream. Sometimes it figures out that it can parallelize. And in fact, the parallelization, in that case, in the case of RumbleDB, is done on top of Apache Spark. So that's nice, right? You've learned Spark. You know data frames, you know RDDs, and it turns out that this is exactly done on top of Spark. But the benefit of RumbleDB is you don't need to learn Spark to use RumbleDB. Of course, you learn Spark because you're master students and you need to also understand how it works, right? But the end user is even shielded from that. Yes, can you maybe pass the microphone?
Then I would like to ask, because in the background, is JSONic converted into Spark RDD execution plan, and that is basically what actually executing?
That's more or less it. Yeah, absolutely.
Okay.
So this whole query plan in there, I will give you the details. In fact, I have more slides, but basically, what you see here is converted to basically Spark transformations on RDDs and data frames. But it's not that simple because it's smarter than that. It's not going to convert everything to Spark transformations because sometimes RumbleDB is smart enough to know that here it's just one value. You want to add a value to another value. In that case, it will know that it doesn't need Spark. It will just nicely materialize the two values, add them on the CPU of your laptop, right? So it's very smart. It switches between Spark or not Spark to find the most efficient optimization. Yes?
Okay, a follow-up question. So after we do this parallel processing, we return the data, we write it to the disk, right? So
you can write it to the disk, you can put it on your screen,
So there wouldn't be a situation where we get like RAM overloaded by the return data. So we basically like flush it all the time to the disk, and that's it.
So if you're afraid of that, you can just spit it on S3 or HDFS, right? If you spit it on S3, it's likely that this is going to be okay. If even spitting it on S3, it's still overwhelming, then maybe you should revise your query because maybe you're too ambitious, right? But if you don't know how much data it's going to be or want to be careful, you can just spit it on the cloud, in cloud storage. Or you can use a limit, right? You can also do limits. I didn't show you, but you can use clauses also in JSONic to restrict to just the first items, right? And then you can slowly, Okay, thank you. All right, so I'm streaming myself back. Okay. All right, so that's actually a good transition because, as I said, you can split the data to S3, to HDFS, not to HTTP. You know, you cannot write to the web, right? You can read, so you can download data from HTTP. Just be aware, S3 HDFS, you will be able to read it in parallel. HTTP is not going to read in parallel. HTTP is just downloading the file and that's it, right? So you need to be careful if you read from HTTP, you will not be able to do it with large files. Local file system, you can also parallelize on your cores, but be careful, you still have a single disk. So the poor little disk is going to be overloaded if you have too much data, right? But you can still do it. Azure, Google, and so on, so you can use any cloud storage. And you can process JSON, CSV, Avro, Parquet, Roots, that's for the physicists at CERN. They love this for finding the Higgs boson. LibSVM is for machine learning and so on. So you have plenty of formats. And again, it's like a Swiss Army knife. You can process all of these. You can read or write to these formats and read or write from these places right here. Now, let me give you a few more details on how this is done, some more of the magic behind that. Because I told you, in some cases, it's going to map it to Spark. In some other cases, it will not. So there is some logic in there in order to make the decisions. It's not perfect. At every release, we try to improve a little bit. It's never going to be perfect, right? Even in a century, it will still not be perfect. In fact, it's an undecidable problem. You're never done with that. Okay, so, well, in some obvious cases, you can see without even executing anything, just looking at the query. You see, for example, somebody doing 2 + 2, right? You see a plus. You know that a plus can only process one item. Remember that, right? Who remembers? Plus needs one item, or 0, but not 2. So if you see a plus, you know that anyway, it's not going to be a billion items in there. So then you can smartly say, okay, the plus, I'm just going to do it in memory, right? So in some simple cases, it's a simple Java method call and that's it, and you're done. In some other cases, like this, it's small enough because there's only 4, it figures out that it's a rather small number. So it's going to iterate. Who knows what a Volcano iterator is? Okay, it's a fancy, I actually didn't know it. It's one of my postdocs who told me that. So Volcano is the name you give to some design pattern in programming languages when you have an API that basically has open, has next, next, reset, and close, right? Who already saw that somewhere? All right, so this is it. This is how we collect the sequences of items. This is one way of doing that locally. We just say open the iterator, has next, yes, then give it to me. Has next, yes, then give it to me with next. Has next, yes, give it to me. Has next, no, okay, I'm done, right? So you just stream your way. This is the streaming I've been telling you about. You stream your way through the data. So that's called the Volcano iterator. You stream your way through it. On the right, this is also small enough that it's going to be using a Volcano iterator, right? So 1 to 10, it's only 10 items. And basically, there is a threshold, I think I set it to 1 million or something, maybe 100,000, that would trigger the use of Spark. At some point, it says, okay, now it's large enough that it's worth creating an RDD, right? But let me do it not with a range, but with an actual file. So let's imagine I open a file from HDFS, from the local file system, from S3, from any cloud storage you want. If I use that function JSON file, it can be messy, right? It's one object per line, but it could be a huge mess in that file. So you cannot create a data frame out of that. You don't know. So it's going to create an RDD of objects. It's polymorphic. It's Java, right? So it's an object-oriented programming language. So there's polymorphism in there. You could have objects, arrays, and so on. It doesn't matter. But it's an RDD of items. So I create an RDD of items. Who remembers what an RDD is? Okay, whew. I was scared for a moment. So you paid attention, right, during the semester. Okay. So we create an RDD of items here. It's Spark, right? So now, how do we execute these dot countries? Imagine that I want to navigate there. Well, in Spark, I can just use a flat map. It's a flat map, and I put in the flat map a function that just takes the object and returns the values after country, right? And I get that, right? So I can implement this navigation right there with some Spark transformation, a flat map. UDF is just a fancy name for user-defined function. It's whatever you feed into the flat map as the way you map, right? Do you have a question? Sorry, I thought you were raising your hand, sorry. We transform from flat map with a flat map from an RDD to an RDD. And now I get an RDD of items. Now you see it's polymorphic because I have an array, an array, an array, a string, an array, a null, and so on, right? Because again, it was a huge mess in here. So this is why. So now we have an RDD of items. What if I do this, right? So now I open my arrays and flatten everything. And that's also going to work, right? Again, I can use a flat map in Spark. And in my UDF, I just say that I output individually each value in there. And since it's a flat map and not just a map, so the flat map will flatten everything like this, all right? And then I can continue with distinct values, for example. Now that's the magic of Spark, because imagine I have a million values in there, and I want the distinct values with my distinct values function. That's a JSONic function. But you know that in Spark, I have the distinct transformation. So RumbleDB figures out that it can use the distinct transformation of Spark in order to evaluate the distinct value JSONic call. For whom is that clear? Right? Okay. There is a name for that. It's called the push down. What basically happens in the brain of RumbleDB is that, oh, the user wants to do a distinct values. I have no idea how to do that, but I know Spark does. So I'm just going to push it down to Spark and let him do it. Okay, so that's called the push down. And the word push down is really important. This is very popular in databases when you have multiple layers of data processing. Push down is, you don't want to do it yourself. You just push it down the stack. You just let some other layer take care of it. And it's very efficient to push things down because you're just bringing the computation closer to where the data is. All right, now what if I open a Parquet file? Well, a Parquet file, they look nice because they're never messy. It's a data frame anyway, it has a beautiful schema, it has the columns. So in that case, we are not going to create an RDD, but we are going to create a data frame directly, right? And you know, in Spark, we do have data frames, right? So now I have my data frames, 3 columns like this. And as a summary, this is what happens. Whenever I have a homogeneous sequence of items. They all follow the same schema, or maybe it's just integers or just strings, or all objects with the same schema, and it's data frame compatible. Then I use a data frame, right? So the user sees that as part of the data model of JSONic, but what's happening behind the scene, hidden from the user, is that there is a data frame. Now, if my sequence is a huge mess, look at this, integer, Boolean, object, array, so that's a huge mess, no problem. We use an RDD of item, and with the power of polymorphism, we can actually fit it all in there. But the nice thing is that physically it's different, but the user doesn't see that. This is all hidden here. The only thing the user sees is that, and this looks the same, these are just sequences of items, right? So we hide all of that is hidden inside RumbleDB. So you see, in RumbleDB, you have full support for the relational algebra. I showed you, you can do selection, projection, grouping, joining. I showed you earlier, right? And I throw at you, just for the sake of showing that to you, this is, I don't even know if that actually means anything. I just wanted to show you that you can actually put that in any order. So look at that, for, it has to be a for and a let at start, right? Let, order by, let, group by, for, count, where, return. You cannot do it in SQL. In JSONic, you can put it in any order as long as it's for or let here and as it's return here. Always indent in a way that this is aligned. Always do that. You're doing yourself a favor. If you do not nicely align all of the clauses that belong together, it's going to be unreadable. And if you nest flower in flower, you're going to be lost. Always align very nicely the clauses that go together, and then you see the flow of tuple streams going down the flow. All right. Here's another example. This time I'm showing you with flower expressions, with the streams of tuples, because so far I explained it with sequences of items. What about tuple streams? So imagine that I open that file. It's a JSON file, so that's going to create an RDD, right? Because it's not a Parquet or CSV, right? So I don't know if it's messy or not. So it's creating an RDD. Now, imagine that this goes in a for clause. Do you remember that when I explained to you how the clauses work in Flower, I had these nice visuals for you? You remember that? They looked like data frames, right? But I told you, be careful, these are not data frames. They just look like them, right? So when you have a for clause, you create a column with the name of the variable, and then on every row, you have one sequence of items, so the current binding. Well, technically, since it's a for clause, it's only going to be one item every time. A let clause is going to add another column. The where clause is going to filter some of the records and so on. Who remembers that? Right. So I told you, no, I didn't see enough reasons. Who remembers these visuals? Okay. So look last week in the recordings again, if you were missing that, but they are visuals. And I told you these look like data frames, but in fact, in RumbleDB, we implement them as data frames. So what's going to happen is that we actually create a data frame with one column called person, but the type of that column is just binary because, again, it's a mess. So the only way we can actually force fit that into a data frame with one column is to hit it with a hammer. So basically, we squeeze it as a binary value. We serialize that JSON as some sort of sequence of bits, and the type of that person column is actually just a binary column. All right? So now that we squeezed it into a column, imagine that I have another for. So now it's going to iterate. You see the second for sees the first for, right? So now I'm going to refer to the first for, and I'm iterating on the countries, only those that are not null. So if there are any nulls, they get thrown away with this. And now you see, I'm going through, I'm iterating. So you see that this is repeated, right? Because again, that was my first value for the first for, but since the second for iterates through the values of the array, you see, I'm just going like this through the array, creating, then I go to the second one and so on and so on. So this is what the two fors are doing. And again, I have one column in my data frame for every variable in there. This is all implemented in Spark SQL, because you remember in Spark, you can manipulate data frames with Spark SQL. RumbleDB actually generates automatic Spark SQL code that implements the logic of that in such a way that it just works. Then I have the where clause. This one is easy. It's a Spark SQL where, in fact. Oh, yeah, go ahead.
Do we need the flatten here?
At which position?
Uh,
Oh, here.
Flatten, yes.
Let me think about that. No, we don't need it. No, you're right. That's actually a very good thing. Yeah, you don't need. It's actually redundant. Flatten would be useful if there are multiple levels and so on. But in that case, you know that it's an array of strings that's already opening the array to return a sequence of strings. So you don't, I could remove that and that would be the same. Yeah, so that's a very good point. Okay, thank you for that. Another question, right? Okay, so now we have Spark SQL, the where clause. Oh, now I have a let. Remember, the let adds a third column. And now, what did I do here? I drank too much orange juice when I was writing that. Okay, so that should obviously be a colon equal and not an EQ. I don't know what happened. And so here you put this person name first. So you see it should match normally in here. All right, and then return. So this was still a clause, so that returns a tuple stream that is implemented as a data frame. The moment the return clause arrives, that has to be now a sequence of items again, because now I have a flower expression. And now you see all of these, because this is return first name. So I'm basically returning that as now a sequence of items. So now it creates back an RDD in that case, okay? An RDD because I don't know if these are all strings. It could be a mess. All right, so technically, of course, it's very complex, right? It's several years of work by 20 people. There is an academic paper that was published in VLDB that you can find the link on the course webpage. You really should read that paper. It's data independence for large messy data sets, Rumble. So you should really read that. This is all explained here. I'm just giving you the overview here and the intuition. So basically, if you have flower expressions, if you're reading from a very large file with billions of values, you're going to be using data frames and the power of Spark. But in some cases, you might have a for loop on a ridiculously small number of values. RumbleDB will see it to say, okay, now that would be ridiculous to use Spark. So in that case, it just iterates locally on just one CPU on your machine in order to do that, right? I mean, look at that. You know that this goes in just a few milliseconds, something like that on the laptop. Imagine the time it would take to set up a Spark cluster and run that in parallel. It's always a call to make, basically. Okay, so this is for the flower expressions. They can either be executed with data frames or locally. Now for the sequence of items, there are several possibilities. So there are the RDD transformations or the data frame transformations. Yes, because if the data is valid, then you use data frames, right? So this is implemented with transformations. This Volcano iterator, it's ridiculously small, so you don't bother with Spark. You just do it literally locally on your CPU. And in the case where it's a single item at a time, it's just a direct Java method call. You don't even need to iterate because it's just one item. In the first versions, we did iterate, but again, it looked ridiculous. Like open, has next, yes, next, give it to me, has next, no, thank you very much, goodbye, right? So it was just an overhead. So now we just directly, when we know it's going to be just a single item, we just call a method and get that item. So it's incredible the performance that we gained just doing that. And in some cases, and that's the magic that we added in the past 2 years, in this case, we can even compile the whole thing as Spark SQL natively, right? And in that case, it doesn't even produce any of this. It just directly writes Spark SQL and manipulates without any binary or any sequence of bytes anywhere. All right. So what happens when you try to run a query is that it parses it. It creates a static context, which is just some compile time information that can help you. It tries to infer the types. That way it detects the places where it's just one item, if it's large or small sequences and so on. Then it determines the execution modes. Should it be an RDD? Should it be a data frame? Should it be a Volcano iteration? Should it be a simple single method call? And then it compiles it to a runtime iterator tree and it gets executed. So this is another example with a query like this. that would lead to that runtime iterator tree. And I nicely draw the colors like sequences of items. And I put in that case what execution mode you will have. You see, it's a huge mix of that. It smartly switches between all the possibilities in order to just do it as fast as possible. This is the beauty of data independence. Without data independence, you will never get that. Data independence gives you the power to put some separation layer with the user, and below the separation layer, you do whatever you want, right? As long as you get the correct results, you can use whatever strategy you want to execute this. This is yet another example, just to show you for a query like that. So in that case, imagine I open my file, could be a mess, so that's an RDD. .foo, that's a flat map. .bar, it's again a flat map, creates an RDD. Here I have another flat map for opening the array. .foo bar is another flat map. And then the sum, push down, you see push down here, because here I will probably get a sequence of integers or a sequence of numbers. And I can actually push that down as a single reduce transformation, right? And then Spark will magically execute that in parallel. So the beauty is that if you have a small file, you can execute that on your laptop. If you have trillions of items sitting on S3 spread over 1,000 files, you can use exactly the same query, and it will just work on a cluster. But the query is the same. Again, that's data independent. It doesn't matter if it's your laptop or a cluster of machines. So the high level view where things, basically now we're looking at the future, right? So this is where things are going. This is really cutting edge, like bleeding edge almost of what we are looking at now. So there's been a paper at the CIDR conference. So the CIDR conference is about the latest innovations in databases. And it's the same people actually who are behind Spark. You probably recognize the names here. We have the CEO and the CTO in here of Databricks. They suggested that instead of having, on the one hand, the relational database management systems, and on the other hand, we have these data warehouses, right? And data warehouses on relational database management systems, on the one hand. On the other hand, we have the data lakes, S3, HDFS, and so on, where we just drop the data as it is, right? And they suggested to unite that on a common framework that has everything, the data warehousing and the data lakes, and they called it with a beautiful name, Data Lakehouse. And now this is kind of, I'm not saying it's like blockchain or, it hasn't reached that status yet, but somehow the lakehouse is a big thing now in the database community.
The question, what does ETL stand for?
ETL. So I will tell you next week. That was my plan. ETL means extract, transform, load. You remember that for data lakes, you just drop your data on S3 or HDFS. If you don't have a data lake, but you have an actual database management system, then you cannot just drop your data. You need to import your data. And ETL is just the fancy way of calling an import, right? Because when you import, you need to extract the data, you need to transform it, and you need to load it into the system, right? Okay. Okay, you can read the paper, actually. It's a good read. So this is the traditional way, and this is what they suggest, where everything is integrated as a lakehouse. And technically, the vision of that is that JSONic is a lakehouse language from the design because of the data independence, because it can process structured data as well as messy data. What we have, in order to get a paper accepted in a conference like SIGMOD or VLDB, there's a secret. You need to have 2 full pages of fancy graphs at the end that show performance. So of course, we needed to add them to the paper, and this is what we got. So here we compared the RumbleDB. It was called Rumble, but then I think Disney made a movie that's called that way, so we couldn't. So we renamed it as RumbleDB. And here we compare it with AsterixDB, which is another database, with Spark SQL, with VxQuery, that is an alternate JSONic representation. CloudDB is a story of its own. It's actually a very well-known vendor of databases, except that in the license, it says you're not allowed to benchmark based on the license you have, so you cannot say it's them. So basically, what people do in database paper is that they give fancy name like CloudDB, And everybody knows, of course, what it is, but you cannot say it for legal reasons. But things are actually changing because now some of the companies started publicly lifting these license terms from their products, and now it will basically accelerate, I think, with the academic community, the ability to benchmark the databases. It's very funny to see the blog posts of Databricks and Snowflake, who are basically just having this battle on social media. It's very entertaining to watch. All right. Now I told you that JSONic can be seen as a lakehouse language, because look what you can do. You can create data, validate it against a schema, and store it in Parquet, in CSV, and so on. I showed you an example. In fact, very often, what do you want to do with this? You want to basically use machine learning, right? Everybody wants to do machine learning. But the problem is that your data is messy, and machine learning needs something structured, like at least the classical machine learning algorithms. So you want your features, you want your labels. And one of the pain points of machine learning is the preparation of data. But with a language like this that allows you to deal with messy data, you can use it to clean up the data, structure it, normalize it, create a table, store it in CSV or one of these formats, and then you can feed it in machine learning, right? So that I already explained to you why it needs to be cleaned up, right? What happens when the data is messy. So this is an example. Don't worry about the details. You can look at it offline. This is the sort of things you can write to clean up your data. So here it's assuming that the data is not very clean. You can use this type switch to basically just turn everything into the same types and so on. I don't want to spend time on that. Just look at it offline. It's just how you would clean things up. And what happened 2 years ago is that I had a brilliant student who actually spent several projects implementing machine learning on top of RumbleDB. So it means that with RumbleDB, after cleaning up, you can actually execute machine learning algorithms in the same engine. And the way it was done is, we don't know the first thing about machine learning, so we just ask Spark to do it. So there is Spark ML, and everything is just pushed down to Spark ML in that way. And so basically, this is what it looks like. You see how you have k-means. In that case, we just create an estimator, and then we say what are the features and so on. I'm not a machine learning expert, so this is as much as you're going to get from me in terms of machine learning. But basically, it's all integrated, and you see that this expands, this whole idea of data independence expands to machine learning, and there is a whole part of the machine learning community that is into declarative machine learning. Like, how do you design machine learning in a way that you don't have to go down into the details? It's very, 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 very difficult, because those of you who know machine learning, you probably know that when you tune the parameters, the hyperparameters, and so on, it's very, very complex. So it's really just an ongoing area of research, right? But that was a nice experiment to just try to forward the machine learning directly to Spark ML. So Spark ML is a machine learning library that Spark has. All right, that actually is my last slide for this lecture. Do we have any questions? Yes, we can go.
Yeah. So my question would involve rather, let's say, philosophical part of this. So when you layer a lot of stuff, a lot of technologies, what shortcomings may there be? Well, in terms of speed, certainly. So because you need to communicate between different layers in a way, but could there be potential data loss between layers? Or so, for instance, when we pre-process before doing machine learning, something maybe, I don't know, we lose some percentage of data because it's not clean enough, not structured enough.
Are you asking in terms of losing because of some mistake in the system design, or just because we on purpose throw away some of the...
Because on purpose.
On purpose?
Yeah.
Yeah. So this is more of a machine learning question. So now you're reaching my limits. But basically, the idea, the way that it all integrates you know, as computer scientists, we design things in a modular way, right? So we have all of these components. In this lecture, I showed you multiple components, right? You have the syntax, the files, the cloud storage, the processing layer, the query language, the indices in the document store, and so on. And this is again part of the design of a larger ecosystem where you also have the machine learning algorithms and so on and so on. So what is crucial is to understand the moving parts of that system and to understand the communication between the layers. If you want a good system, you really, really need to make sure that every single component in your system has a well-documented behavior, right? It says exactly what input it expects, what output it promises to give you. It might also say that some things are undefined, then you should not rely on them. But basically, this is a prerequisite. And this is how you can then orchestrate the whole things. And big data is really about mastering all of these components and knowing which ones to put together. So if you lose data, you just need to make sure you're in control. So if you as a database person, my job is to build an engine that will not lose data in a way that is not on purpose, right? I have to make sure that all the data flows. Then if the user decides to throw data it doesn't need because of machine learning consideration, at least they have the control. Unless maybe there is another system that would do it differently, right? Did I make any sense?
Yeah, definitely.
Okay, you're pushing me to my limits, right? Again, I warn you, I'm not a machine learning person, so.
But can there be problem with interaction? So with interaction. So say we have a well-structured docs, we have well-defined APIs, that's it. But when we put things together, sometimes it may break.
Yeah, you really need to make sure.
Yeah.
So I think what you might be addressing has a name, it's called impedance mismatch.
Yeah.
And impedance mismatch makes things very complicated. Let me give you examples of impedance mismatches. You're building a website, you're using maybe Java EE or Python, and you're using SQL. The types that you're going to have in a relational database management systems are going to be kind of, sort of, but not exactly the types that you have in Java. I showed you these mapping tables. This is called an impedance mismatch. And every time you have these interfaces, you really need to sit for an hour, go through the types, try to see, try to match that and try to either do it lossless or in a way that you document the loss. But the impedance mismatches are a real problem that really adds complexity to the system. And so, yes, you're absolutely correct that this is absolutely crucial. And whenever you have two systems that may not have exactly the same types, you really need to take an hour and sit down and figure it out, because you're absolutely correct. Otherwise, you might have surprises.
Thank you very much.
Okay, thank you. We have 2 more minutes. Any other questions? Okay, then I will ask you a question then. So according to Murphy's law, the moment I do that, it's going, yes, exactly. So, oh no, actually directly. Awesome. So just tell me, just so that I see. Very good. That's good. Okay. Okay. Okay, now that I talk about Netflix series, you want to need to keep each balance, right? Okay. All right, very good. But at least it's above 50%. My recommendation is very, very simple. Write JSONic. Download the data sets, run the exercises. All past exams are available, so solve it and make sure that you master JSONic, right? All the rest is theoretical. We are not going to ask you to implement an engine, but JSONic, you really need to take the time to be comfortable. with writing queries. And of course, we have a TA team who worked on the exercises that you're going to get. So really take the time to solve them. All right. Thank you very much, everybody, and see you tomorrow, 9 a.m. We are going to talk about graphs tomorrow. So see you. Thank you.